So for those of you who are new to IARPC, IARPC is the Interagency Arctic Research Policy Committee and brings together leaders from about 18 agencies, departments, and offices across the U.S. federal government to enhance collaboration on research in the Arctic. IARPC Collaborations is the public branch of IARPC, and it aims to facilitate interagency communication, coordination, and collaboration to advance Arctic science. So a couple of years ago, IARPC released its Arctic Research Plan 2022-2026, and IARPC is currently preparing for its second biennial implementation plan. So you'll probably receive some notifications about that. So the Physical Oceanography Community of Practice aims to facilitate the exchange of information and also encourage new collaborations regarding physical oceanography of the Arctic Ocean across agencies, primarily through the organization of monthly webinars like this one. So a session last month featured two presentations focusing on the atmospheric boundary layer as it is relating to the ocean and sea ice. But today we will be focusing on the oceanic boundary layer of the Arctic Ocean itself. We'll have two presentations that approach the system from a complementary perspective. So first, Sam Brenner will discuss the interaction between the atmosphere, ocean, and sea ice, mostly from an observational perspective, whereas Kat Smith will focus on understanding the oceanic boundary layer from a numerical modeling point of view. So we'll start off with a presentation by Sam Brenner, who is a postdoc at Brown University, where he's working in a group of Chris Horvath. He received his PhD in physical oceanography from the University of Washington in 2022. And the title of his presentation is How Sea Ice Modulates Stress Transfer into the Ocean Boundary Layer. So with that, take it away, Sam. Looking forward to your presentation.
Great, thank you. Just doing the window shuffling thing that always happens at the beginning of sharing slides. So bear with me a second. And hopefully everybody can see my slides.
Yep.
Perfect.
Great.
Okay. Okay, I'll get going then. Yeah, so as you just heard, my name's Sam Brenner and I'm a postdoc at Brown University. The work that I'm going to show today, though, is largely from my PhD at the University of Washington, and I'm going to give some perspectives of how sea ice modulates stress transfer into the ocean boundary layer. And this is, not a complete picture. It's a complicated system, but hopefully we learn a few things here along the way. And I'm going to do something a little bit different in terms of motivating the talk. Instead of showing a lot of background, I'm going to zoom in on a really specific event. And this is an event that's part of some in-progress work that I'm doing with Ed Blanchard-Rigglesworth and others. And this is looking at a sea ice loss during a really extreme cyclone in the Barents Sea in 2022. And so this map on the side here shows the change in sea ice concentration over a roughly 1 week period in January, where there was this really large cyclone that came through. And so the black contours here are the sea level pressure of that cyclone, and it sort of came up and was centered on the Barents Sea. And there was just a really massive loss of sea ice. And by some metrics, this was the largest 1 week decrease in sea ice area in the Arctic over a 1 week period in the satellite record. But this event happened in January. It was the winter. It was really, really cold. And so there wasn't, even with the cyclone, there wasn't actually much heat in the atmosphere to cause this melting. And so the melting had to come from below. The heat came from the ocean. And so luckily there was an Argo float in the region at the time, and we were able to see in these temperature salinity profiles signs of this upward mixing of subsurface heat. And so you can see in the blue line here is the temperature and salinity profiles before the cyclone, and the red is after. And so there's this really big decrease in the heat in the ocean. And that amount of heat loss translated to the sea ice loss we saw. And so this is kind of an example. I wanted to start with this as a motivational thing, because it's an example of how important the upper ocean is, and the structure and the interconnectedness between the sea ice and the upper ocean. And of course, the climate is shifting and sea ice conditions are changing. And so these types of coupling between the atmosphere and the sea ice in the ocean are also going to change as well, and that's going to have implications for how these events play out in the future. Okay, so zooming back out a little bit, we can broadly say that the type of vertical mixing that I was just showing is kind of a competition between stress and stratification. And sea ice impacts the air-sea momentum transfer, so it modulates that stress that's available for mixing. And importantly, something that happens in sea ice that's different from the open ocean is that there are these internal stress terms within the sea ice itself that can act as a sink of momentum as the stress is transferred from the atmosphere into the ocean. And so because of that, there's this view that as we get into a more seasonal sea ice regime, there's going to be this increase of open water, and that's going to lead to more efficient air-sea coupling in the future. So the stuff I'm going to present today is trying to understand this progression a little bit. And what I'll actually suggest at the end of the talk is that it's less about this open water and actually more about a shift to a weakening of the mechanical strength of the sea ice and a decrease in these internal stress terms that are actually potentially going to have a bigger impact on future conditions of air-sea coupling. Okay, so for the rest of the talk, I'm going to forget about that cyclone, and I'm going to move across the Arctic to the Beaufort Sea in the Western Arctic, this region here. And I'm going to focus on some observations that we made in over a one-year period from 2018 to 2019. And there's a whole bunch of different ways that we can measure the ice-ocean boundary layer, and a lot of those different methods have different advantages as well as different challenges. And so today, the ones that I'm going to be showing are made from a set of moorings that we installed, as I said, for a year in this sort of roughly north-south line in the Canada Basin. And the advantage of having these moorings, and this is just a schematic of what those moorings look like, the advantage of having these sort of moorings, these fixed in place measurements, is that we get a view as the ice changes and advances and melts throughout the season. We have this really wide range of different surface conditions that we're able to measure against. And that includes measurements in the southern part of the domain in the seasonally ice-covered waters, but in the northern part of the domain, this northernmost mooring was in perennial sea ice. It was deployed and recovered through the ice. And there's a variety of measurements that we made from the moorings, but what I'm going to sort of focus on today is the upper ocean velocity. And there's a lot going on when we start looking at the observations of the upper ocean velocity. We could a lot of different things that we can talk about when we examine this. One of the things that I'm going to focus on are just one part of the story, which is these inertial oscillations that you can see here. And so these vertical stripes back and forth, vertically coherent, are examples of inertial oscillations. And we see these throughout the year, even underneath the ice, at all three of these different moorings. And inertial oscillations are really useful for understanding stress transfer because they can help think about how that stress transfer is impacted by the ice. And the reason for that is because there's really direct relationships between the wind forcing and the inertial oscillations. And so sort of schematically down here, these inertial oscillations are part of a transient response. If the wind speed changes, you get this sort of transient adjustment to a mean state. And so there's this really nice link. And so if that link is disrupted, by the sea ice, we can see it. And the other nice thing about them is that the physics that describe the inertial oscillations to some extent are relatively simple. And so we can make use of that to better understand some of our observations. Another nice thing about the inertial oscillations that we can use to our advantage is the fact that they are relatively homogeneous within the mixed layer. So there's a pretty low shear within the inertially filtered time band within the mixed layer, and that's followed by then a peak of the shear below the mixed layer. And we can use that, or we have been able to use that together with other data from the moorings to reconstruct time series of mixed layer depth at each of the moorings, which especially is advantageous as we switch from sort of deeper winter mixed layers to summer mixed layers where you have this shoaling of the mixed layer depth, and that's not necessarily captured by the temperature and salinity sensors on the moorings because the mixed layer becomes too shallow to see them. Okay, so what I'm showing here is a time series of the inertial oscillation strength at each of the moorings in these depth with time panels at the bottom here. And what we see in these is that all three of the moorings, the inertial oscillation strength has this really pronounced seasonality. Underneath the pack ice, in the center of the period here, you can see the ice concentration in these little bars at the top. Underneath the pack ice, we have really weak inertial currents and a deeper mixed layer. And then as we shift into the summer period, when we have a shallower mixed layer and we shift to more marginal and ice and open water, there's this increase in the inertial current strength. And this seasonality isn't something new. This is something that's been seen for a while. This is consistent with observations that people have been making of inertial oscillations for a while. And it's one of the classic lines of evidence about sea ice reducing stress transfer into the ocean. If we take all that data together and we bin it by sea ice concentration, we see, as expected, that there's a major reduction in the inertial current strength for high ice concentrations, about an 80% decrease in the oscillation strength. But there's actually no discernible differences between the open water and the marginal ice conditions here. Both of these have kind of, on average, there's some spread around here, but on average, the same inertial current strength. But I want to go back to this figure for a second and point out that these changes in sea ice concentration are really highly correlated with these changes in mixed layer depth, because you get these shallow meltwater-driven mixed layers in the summer. And because inertial oscillations can be constrained by the mixed layer depth, we need to take that into account when making these types of plots and comparisons. And so if we account for that, there's different ways we can think about doing this, but just as an example, if we do some sort of normalization by the mixed layer depth, then we see that the inertial oscillation strength, there still is a decrease at high ice concentrations, but that's not as profound as before. So before we had about an 80% decrease in the inertial oscillation strength. But when you account for the changes in mixed layer depth, that drops to about a 55% decrease in inertial oscillation strength. So ice is having a major effect, but it's not only the ice that's having an effect here. And we have to take into account the ocean structure when we're thinking about how the ocean velocity changes and how to interpret those changes in the frame of sea ice concentration changes. So as I said, the relative simplicity of the inertial oscillations is great because it lets us investigate counterfactuals. We can ask, what if the ice wasn't there? What if the ice didn't matter? And this is really nicely demonstrated as an example in this case study that's being led by my colleague, Laura Cruz. And she's looking at a storm event that occurred during this measurement record. And the storm event was in February 2019. And the wind speeds and the sea ice drift speeds across the mooring array were really similar during that event. But what we saw is that the inertial response at the different moorings was really different. And so it's possible to estimate the potential strength of these inertial oscillations if the ice that was present had no internal stress damping effect. In that case, and that's what is shown here as a mixed layer average, inertial current in these dotted lines at the top here is the potential strength of the inertial oscillations. But the observations here at this northern mooring showed that the inertial oscillations were much weaker than what they potentially could have been if the ice didn't have an effect. And so that's telling us that the ice had a really strong impact on reducing the strength of the inertial oscillations, in this case, by about 80%. But at the southern mooring, the ice didn't really have a major impact. You can barely see, but those same dotted lines are here in the background. But the observations of the inertial oscillations really closely match those dotted lines. So the oscillations were relatively undamped by the ice here. So Laura found imagery of what the ice looked like just before the storm. And what we see is that in the southern part of the domain where this southern mooring is, the ice is really heavily fractured. You can see these sort of bright lines are leads and cracks and fractures in the ice. And so we think that all of this fracturing in the southern part of the domain means that the ice was mechanically weaker. And so that isn't present in the northern part of the domain. So even though the ice concentration was still near 100%, for both of these two moorings, it's this mechanical weakness that allowed the oscillations to persist undamped. So I did a similar type of analysis throughout the full record of the moorings. And what I'm showing here is a histogram of the ratio of the inertial oscillation strength in a scenario with ice versus without ice. And I'll admit there's a little bit of sleight of hand here. This isn't exactly the comparison that Laura was making, but it's in the same type of vein. And in this histogram, values of this ratio that are less than 1 show that the ice reduces the oscillation strength. And just like in that case study, we see that there's a big peak here for this northern mooring in yellow at something like 0.2, like so about 20%. And so that's, again, a reduction of about 80% in the oscillations. And so, again, this reinforces this idea that internal stresses act as a sink of momentum. But if we look sort of at all of the different data here, we actually see that there's a lot of data on this side of the plot. And so that's values above 1, and that's showing that ice actually acts to enhance or amplify the total stress into the ocean relative to if there was no ice. And that's particularly true for the southern mooring that I'm showing with the blue bars here. And again, that's sort of linked to this idea of this mechanically weak sea ice. So if the mechanically weak sea ice is actually able to really efficiently transfer momentum from the atmosphere ice boundary layer into the ocean. And we get differences there's differences in the surface roughness between the ice surface and the ocean surface. And so the stress, the atmosphere ice stress is higher than equivalent atmosphere ocean stress. And so if the ice doesn't damp that stress out because it's mechanically weak, then you have the opportunity for enhancement of the total stress into the ocean. So there's these different kind of competing factors that are at play. So all of that was focused on just the inertial frequency. It's really nice to think about the inertial oscillations as sort of this marker of stress transfer. But they're not the only type of motion that's going on. So the last idea that I'm just going to hopefully end with here is looking at the subinertial response or the non-inertial response. And when we look at that, we were actually fairly surprised to see that there doesn't seem to be a big impact of the sea ice. And so here on the left, I'm showing the same sort of bin average by sea ice concentration of the Ekman transport that's calculated from our best guess of the total surface stress. And here I'm showing the depth integrated non-inertial speed in the mixed layer. And I'm integrating with the mixed layer over the mixed layer depth to sort of account for that seasonality in mixed layer depth that we saw. And when you take that into account, you can see in both of these cases that there's really no dependence on sea ice concentration, and there's no drop off at high sea ice concentrations that we saw before. This is kind of surprising to us, and probably needs a little bit more study to fully understand. But it's an interesting result. Okay, so hopefully I'm close to on time here, but I'll just leave a couple of takeaways. One is just that when we're interpreting observations in general, there's a bunch of things that can impact those observations. And so in particular, we need to account for ocean structure when we're interpreting seasonal variations in any sort of metrics of ice-ocean coupling. And here, especially the mixed layer depth is a really important control on that oscillation strength. And so if we don't take that into account, then we might sort of put too much onus on the importance of the sea ice. We could see that the shift to more marginal and weaker sea ice may be more impactful on ocean surface stress changes than just a shift to open water. And if we compare the different moorings, it seems that the sea ice mechanical strength is potentially already playing a decreasing role in the dynamics at that southern mooring where the ice is younger and thinner. Although there could also be some other geographic types of constraints leading to the increased fracturing and leads down there. And so finally, we didn't see a strong ice concentration effect on the calculated Ekman transport or mixed layer integrated non-inertial or low frequency velocity. And that suggests that the sea ice might act more like a low pass filter on the ice ocean stress transfer rather than just a sort of flat damping effect. We don't know if that's an emerging feature of the shift to more seasonal ice. It's certainly not consistent with what people have talked about in terms of those types of observations before. And so I think a little bit more work is still needed there to understand how robust that result is and to see what that means in a more general framework. So I will end my talk there, and I think we can move on to Kat's talk. Thanks.
Hey, thanks so much, Sam. It was an excellent presentation, very, very insightful. We'll have a discussion, broader discussion after Kat's talk, but maybe we'll have a couple of minutes for quick Q&A for Sam. Please raise your hand if you have a question. Maybe I'll start off with maybe John will start it off with the question. John.
Hi, John.
Nice talk. Very quickly, does your Ekman transport include the mass transport of the ice?
No, I should probably
because you could just do the vertical integral. It doesn't, as long as there's no internal ice stress, you're perfectly valid to go from the wind stress down to the deep ocean to get that ageostrophic transport.
Yeah, okay. That's a good thing to check.
Yeah.
Thanks. I'll look at it.
Are there any more questions? I had a question, Sam. I understand that the inertial oscillations in the Arctic are very close to major tidal constituents.
Yes.
And so how do you deal with that?
Yeah, that's definitely a challenge. One of the Beaufort Sea, the tides are fairly weak. And the inertial oscillations obviously have this polarization. And so I kind of just ignored the tides and just made sure that I just took the clockwise part of the oscillations. And so that's what I did in most of my analysis. The work that I was showing from Laura Cruz, she's been a little bit more careful than I have. And so she actually found a tidal model and subtracted the model tidal velocities as well. But in the Beaufort, those were relatively small. I think that if we were to try to, do the same type of analysis in the Barents Sea, for example, there the tides are pretty strong. And so you're going to end up having some issues separating those effects.
Great, thank you. And anybody else? Maybe we should hand it over to Kat. So Kat Smith is a staff scientist at Los Alamos National Laboratory. She received her PhD from the University of Colorado Boulder in 2017. And before coming to LANL, she did a postdoc at the University of Cambridge in the United Kingdom. And so the title of her talk is Understanding Physical Mechanisms of Upper Ocean Mixing in the Arctic. Take it away, Kat.
Great, thanks. Can you guys see my slides and hear me?
Yes, we can.
Okay, great. All right, so this work is done as a part of the Interface project, which is the interdisciplinary research for Arctic coastal ecosystems or environments. And it's a U.S. Department of Energy project that's a collaboration between several labs and the University of Alaska in Fairbanks. So I'm sure I probably don't need to give background and motivation for this, but I will give it anyways, just to kind of set up what I'm going to be talking about today. So sea ice has historically buffered the Arctic Ocean's surface layer from both the atmosphere forcing and also from the warm, salty Atlantic water below or Pacific water below. And this in turn influences the sea ice melt rates as well. Right, and this layer is really important. This cold freshwater layer is really important for many physical, chemical, and biological processes. And not only does it have regional and pan-Arctic effects, but it can also have global effects. The first one off the top of my mind that I can think of is the Atlantic meridional overturning circulation. So if we want to have accurate predictions of the future climate, we need to have accurate assessments of this upper ocean stratification in the Arctic and how it's going to change in the future. So sadly, Arctic sea ice is in decline and ice-free periods are increasing, right? And we know this. And so as Arctic sea ice cover declines or goes down, its exposure to the atmospheric forcing is going up. And so a question to ask would be, how is that going to impact the vertical exchange of heat and nutrients from below into the surface layer of the ocean? And then how is that in turn going to affect sea ice melt rates? Two questions that I'm going to try to at least answer in part here in this talk is, first, what are the dominant mechanisms of vertical heat transport and mixing in the Arctic? Are they universal across Arctic regimes? The Canadian basin is quite different from the Eurasian basin, and even then within both of those, there's changes. And then how will these change in the future when we have less sea ice and it becomes more seasonal? And then the second question is, are these mechanisms actually captured by parameterizations? Most of the parameterizations have been validated for mid-latitudes, so temperature-dominated oceans, whereas the poles and the high latitudes tend to be more salinity-dominated oceans. So to answer these questions, I'm using large eddy simulations, relatively idealized in that we're just applying a constant surface forcing to the top of the domain. It's a 3D periodic domain in the horizontal, and we'll run them for 5 days, and we have Arctic-like initial conditions that we have chosen. The domain is relatively small. It's just 130 meters in each direction, with a half a meter resolution. That gives us what we call resolved LES simulations, meaning that the subgrid scale fluxes are an order of magnitude.
Let's mute this.
Hello? Sorry. Okay. It just means that the unresolved fluxes are an order of magnitude smaller than the resolved fluxes. Okay, so the initial conditions we grabbed from the ice tether profilers. I grabbed 2 different ITB drift tracks, one from the Canadian basin and one from the Eurasian basin. So in the right-hand plot and the top panel, we see the Canadian basin, and all of the light gray thin lines are the profiles. And we just took, we basically fitted a polynomial to that to come up with some kind of initial condition. And this is a year-long, in the top panel, that's a year's worth of data that we're using to make the initial conditions. And it's relatively strong stratification for most of the year. Whereas the bottom panel, the Eurasian basin, I will admit, I kind of cherry-picked a portion of the profile in which it had a weaker stratification profile. So obviously it can get stronger stratification than this, but I wanted to compare and contrast a weak stratification versus a strong stratification here. So for forcing conditions, we're using NSAP reanalysis data for it's pretty much the same for both locations, or at least the max and mins are pretty similar. And then we span a surface shear stress and surface buoyancy forcing space to kind of get an idea of what we're the full range. And we do this by applying a surface cooling, a wind stress at the surface, an evaporation stress, or sorry, evaporation, a land fast ice, and a drifting sea ice case. And then I just want to point out that for both of the ice cases, we use a melt parameterization according to McPhee et al. 1987. So I'm not including any thermodynamic feedbacks. There's no internal stresses, anything like that. So it's relatively simplistic. And then the drift speeds for the sea ice work came from the ITP tracks. So this is a table of the simulations. You don't have to digest all of this. I just want to use this to kind of show to you in all the plots coming up. I'm going to organize them according to 3 different categories. So the ones here, the first category is the single forcing cases. Those are the ones where I only apply one type of forcing. So either cooling at the surface, evaporation, or wind at the surface. We have our multi-forcing cases. So those are combinations of the single forcing cases. And then we have ice-covered cases. So both what we're calling land-fast ice, or so a stationary ice case, and 3 different ones with drifting speeds to them. So I just want to clarify here that all the single forcing and the multi-forcing cases do not have ice cover on them. And the idea here is to understand how the reduction in sea ice is going to really affect the surface layer. And then additionally, I'm only going to show one of them in each of the categories, so the strongest in each of the categories, just to kind of, make the plots nice and easy to digest. Okay, so the first question was, what are the dominant mechanisms of vertical heat transport and mixing in the Arctic? Right, so we can start by looking at the mean profiles. So these are mean profiles of salinity on day 5 of the simulations. And the first thing you'll notice is that the weaker stratification, oh, sorry, I should go back. So the top row is the Canadian basin, and the bottom row is all the Eurasian basin simulations. First column is the single forcing cases, so that's the wind, evaporation, and cooling. Middle row is the multi-forcing cases, and then the last row, or sorry, the last column is the ice-covered cases. So first you'll notice that the weaker stratification in the Eurasian basin gives way to a lot more mixing, even with sea ice cover, right? So the effects of these forcings on the weaker stratification is much stronger. 2, without sea ice, salt-driven convection and wind-driven shear forcing erodes the stratification profile. And in fact, the salt-driven convection, at least in these cases, seems to be a little bit stronger than the wind. With sea ice, we actually see that momentum transfer from the drifting ice produces as much mixing as the wind. So we see here that the green line and the pink line are relatively similar in terms of mixed layer depths. So we're getting as much mixing between the two. A caveat here again is that we're not using internal stresses, things like that. Then again, we're also not having inertial oscillations. So I don't know if it's necessarily a direct parallel to what Sam was talking about. And then lastly, salinity and not temperature dictates the maintenance or erosion of the stratification profile here. So you'll see the blue line in the bottom left-hand panel, and then the blue line in the top right-hand panel, which is covered by the green line. Not really much happens with that in the 5 days of the simulation. I'm not showing the plots here of heat flux and TKE budgets, but this additionally kind of supports this argument in that the salinity portion of the buoyancy term for each of those budgets is dominant in that case. So the salinity is really what matters here. Okay, so next we'll look at heat entrainment into the mixed layer. So this plot is a change in mixed layer heat content over the course of the 5 days. And so this includes both change in the heat content and also includes the change in the mixed layer depth over the course of the simulations. And what I'm plotting here is actually the percent change in the the change in the heat in the mixed layer, just to kind of, the mixed layer depths are different between the two cases. And so this kind of evens them out a little bit. Again, first column is single forcing, middle one is multi-forcing, and the last one is ice covered. Solid lines are the Canadian basin and dashed lines are the Eurasian basin. So again, the first thing we see is the much less heat entrainment into the Canadian basin versus the Eurasian basin. And this is primarily because we're not getting as much erosion of that stratification profile, even though the heat that's contained underneath the Eurasian basin is less than the amount that's in the Canadian basin case. Second, we see that drifting sea ice entrains as much heat as moderate winds. Again, caveat, we don't have this is a relatively simplistic sea ice model, and also the other thing I want to say is that these are, I would call, moderate winds. So above this wind speed, I think you'd likely start to see, wave production and wind capping and or white capping and things like that. So I didn't want to go too much further. So this is a moderate wind speed, and so you might see a greater effect of wind if you had more storm-like magnitudes in wind. And then lastly, the salt-driven convection is the dominant mechanism of heat entrainment into the mixed layer. So you'll see here in the leftmost panel, the orange lines, both the dashed and the solid, are sitting above their respective basin counterparts in there. And then also the brown and red lines in the middle panel as well. And so those that have the evaporation in them, so the salt-driven convection is really the dominant heat mechanism for heat transport or heat entrainment, at least in these cases. So what we see here is that the salinity stratification buffer erodes, that drives heat into the mixed layer, and presumably, although we don't have this kind of feedback, that's going to drive more heat, sea ice loss, and less sea ice growth in the future. Okay, so that was the first question. The second question is, are these mechanisms captured by parameterizations? And so we did a really simple column model with KPP in it. And what we're seeing here is, so the top row is, again, is the Canadian Basin case, and the bottom row is the Eurasian Basin case. First column is a cooling case, and the second column is the wind case. And what we see in the Canadian Basin run, I think, oh, sorry, the blue is the LES and the orange is the KPP, single column model. And I think in the Canadian Basin one, we're seeing, you know, it's not doing too bad of a job. Then again, not really much is happening. You could argue that it's mixing a little bit too much in there as well, but it's not terribly bad. And then if you go into the Eurasian Basin, we can definitely see that KPP is mixing way too much in both of these cases. You know, we're seeing mixed layer depths on the order of 5 to 10 meters, you know, too large comparison to the LES models. What's next on this is I should do an evaporation one, but I haven't gotten to that yet. So, okay, so I'll wrap that up with conclusions. So what are the dominant mechanisms of vertical heat transport and mixing in the Arctic? Well, we see that the weaker stratification in the Eurasian Basin gives way to a lot more mixing and heat entrainment into the mixed layer. And we see that wind, salt-driven convection, and drifting of sea ice are all dominant mechanisms of mixing and vertical heat transport in the Arctic across both basins, although the magnitude of that mechanism or that mixing is different between the two cases. And then are these mechanisms captured by parameterizations? KPP mixes a little bit too much for both of the cases that I tested so far. Hopefully we'll have some more cases coming up. Next steps. We want to I'm actually currently examining the role of inertial oscillations, tides, and some mesoscales, since they've all been speculated to be big or potentially important processes for vertical mixing in the Arctic. Hopefully we'll have some results on that soon. And then additionally, I've also added nutrient-like tracers to each of these cases. It's very idealized in that they just have the same profile as the salinity, 0 in the mixed layer and 1 at depth. But that's just basically so that we can start to look at the effects on Arctic biogeochemistry. And that's all I have.
Perfect. Thanks, Kat. Really, really great presentation. Thank you. I'm sure there are questions for Kat, or otherwise we'll also open the floor for more general discussions based on both Kat and Sam's presentation. John, you don't have your hand raised yet.
Just trying to formulate my question for Kat. Again, nice talk. Pardon my ignorance, but have you looked into the scales of the eddies that are presented or created in your mixed layer in your LES? I ask because Sylvia and us are poised to put an ADCP on a profiler rather than a single point current meter. And one of the things we're talking about doing is parking the instrument in the mixed layer and doing a velocity profile measurements. And we're curious to think about the vertical scales that we might want to resolve.
Yeah, that is something that I have started to look at. I don't have plots for you right now, and I don't have numbers, but that is definitely something I've started to do, looking at spectra and link scales.
Yeah, because the rule of thumb I've been sort of thinking about is that the dominant eddies have a aspect ratio and a scale comparable to the mixed layer.
Yeah.
Mixed layer depth.
Yeah, I think
so I don't know if that's true or not.
Yeah, looking at just eyeballing the slices through the mixed layer, I would say I think that's definitely true for the convective evaporation cases. Off the top of my head, I don't know if that's true for the shear cases, but I'll have to look at. But yeah, I'll once I calculate that and have a good numbers for that, I can let you know.
Great. Thank you.
Alice.
I just had a quick question. Could you say a little bit more about your drifting sea ice? Just to have an understanding of, is it simply sort of aimed at or simply represented as a surface stress that's continuously in one direction, or I didn't catch the details of that.
Yeah, so it's just based upon a Dirichlet boundary condition on the top with a roughness to it. And it's just in one direction, right? So this would not capture inertial oscillations and things like, that kind of, or like changes in wind speed and things like that. So we don't expect to see that, but hopefully that's something that we will get to at some point.
Okay, great, thanks.
Just to clarify a little bit more, Kat, so is the wind driven simulation and the sea ice driven circulation, are they identical, or how do they differ?
Oh, in terms of, yeah, so no, the way that I chose the magnitude, so one, you could do, you can set up these simulations in two ways. One that would presumably inject the same amount of momentum into the surface as each other, or the way that I chose to do it was I chose realistic values for the Arctic in terms of, so the wind speeds were the greater, the higher end of the wind speeds that I would see in the Arctic, and then the ice drifting was the higher end of the ice drifting. And so no, they don't necessarily correspond to the same momentum injection in terms, or like the same atmospheric conditions, if that makes sense. But I could definitely see a benefit to looking at, pairing those together such that the wind speed and the ice would be the same case. That could be definitely something we could add to it for sure. Yeah.
Presumably a different drag coefficient. Air to water versus ice to water.
Yeah, and it is, yeah. So okay. Yep.
Great. Are there any more questions? I had one more about your evaporation run. So first of all, can it be considered equivalent to like a brine rejection situation? That's my first question. And the second one, we really don't think a lot about evaporation from the Arctic Ocean. So how important is that process in particular? If you have any thoughts on that?
Yeah. So I guess you could think of it as a brine rejection. It's not, in that it doesn't come with the fresh water or like the cold water that comes with it. So the one that's more probably has brine rejection in it is the sea ice drifting case that the pink line in the Eurasian Basin one, that was actually melting, there was melting along with the drifting of the ice. And so that one was, or sorry, not melting. There was refreezing, or so it was rejecting salinity at the same time. So that that one's a brine rejection, I guess, case as well. So something to do in the future is to kind of pair, or to pull out what part of that is the salinity part and what part is the momentum from the ice drag. The evaporation case, you could think of it in a way that it's similar to brine rejection, but again, it has no sea ice on the top of it. I guess I would think of it as just, latent heat evaporation type case, which, so from the NSEP reanalysis, I chose evaporation numbers or evaporation cases from NSEP reanalysis latent heat estimations. So that's should be appropriate for what's in the Arctic. So, but maybe it's not. Maybe because of the ice cover historically, the ice cover, we haven't thought about it as much. But yeah.
Mm-hmm. Oh, thank you. Thank you. I also still have a question for Sam about the damping of inertial oscillations once they are excited, especially related to the damping effect of sea ice then on the ocean. And I was wondering if you could comment on that.
Yeah, so I can tell you what I think is happening, and I think it's what other literature has said as well, but I think that it's a little bit, maybe there's others that understand it. Maybe John knows better than I do. But the way that I picture it is, so the wind is pushing on the ice, and the ice moves, and it then pushes onto the ocean underneath. And so that excites the oscillations. And the ocean then has, some sort of time frame over which those oscillations would be damped down if there's no ice. But the presence of the ice means that they're damped down much faster. And that's because those oscillations that we see in the ocean are also true like of the ice itself. There's inertial oscillations of the ice, and those two match really closely together. So you sort of have the wind pushing on the ice, pushing on the ocean, but then it's actually the ocean, the oscillations in the ocean are what's driving the ice motion. And if these inertial stresses, or sorry, internal stresses are preventing that movement of the ice, then you suddenly like lock it into place and you create shear between the ocean and the ice. So the ocean is still going to be trying to move, but the shear, it then acts to like pull energy out of the ocean. And then that leads to the damping of the oscillations. So hopefully that makes sense. But it's this weird sort of like it goes through and then comes back out the other way.
Right. Yeah, very interesting. So do you have any idea of the time scale of decay, typical time scale of decay of inertial oscillations through a process like that?
Yeah, so, you know, people talk about these oscillations in terms of time scales, and in the open ocean, you know, different numbers get thrown around, but something like on the order of 5 days or something, 5 or 6 days is something that is commonly said for the open ocean. If we look at the time scales that we see in the open water part of the observations, it's a little bit slower than that. And that could be because of differences in like the beta effect and the pumping of internal waves from those oscillations is a little bit different in the Arctic. But then when you start putting the ice on top, the time scales stop being measured in days and start being measured in like hours. So it's a really sort of dramatic effect. So you like the typical slab model type of model for the inertial oscillations in the ocean has a just a linear damping term. The inverse of that damping term is the time scale. And so what we do in our work is we have coupled ice model and ocean model. They both have linear damping terms. Those damping terms are not equal to each other. So the ocean damping term is still like 5 to 10 days or something, but the ice damping term varies with the ice concentration and is something like hours to a day or even less.
Mm-hmm. Cool, very interesting. Thank you. Are there any more questions? Maybe I'll just try to see if we can tie things together. I mean, we have seen kind of really state-of-the-art observational as well as modeling studies. Sam, as mostly focusing on the observations, what would you like to take out from a model that Kat has been showing results from that would help you, and the other way around? Kat, what kind of information could you use that Sam has presented that would be useful for your studies? And let's start with Sam first.
Yeah, that's a great question. I think it's first of all, it's just so cool to see the work that Kat is doing. I think that observations are challenging, and as I said at the beginning, there's sort of different ways that we do them that have different advantages and disadvantages. And one of the disadvantages of these moorings, even though they're great for getting a wide range of different sea ice conditions, you don't get a lot of detail like right near the ice. There's blanking distances and things like that, and side lobe reflection distances from the ADCPs and these other things, sort of right in the most important and most interesting part of the boundary layer. So it's cool to be able to, like with the modeling work, to still look across a really wide range of different sea ice and open water conditions and surface types. But think about like what's happening in those details that we're missing, and also how do those mixing sort of events at the base of the mix layer proceed, and can maybe give us some ideas. Even just going back to John's question, like how do we design better measurements to be able to see those effects?
Yeah, I would say, well, one, I think Sam and I talked at Ocean Sciences 2 weeks ago about, what he was going to present today. And actually that gave me ideas in terms of, so the observations he's already done have given me ideas in terms of, examining the internal stresses and that kind of thing, and the dampening of the sea ice. And I think that's all really great. I think I have a soft spot for biogeochemistry, just anywhere in the ocean, but it's, the Arctic as well. So like, even though it's probably not Sam's, specialty, but more biogeochemistry measurements would be really great, but I understand that in general, it's hard to observe the Arctic in many ways, so, yeah.
All right, wonderful. Well, thank you very much. If there's no further questions, then maybe we can conclude it. I'll hand it off to Tony in a little bit. Just to announce, we'll have no meeting in April planned, but we do have one for May, in which case we will be talking about the SASE project, and then we'll have a session on Cook Inlet in June. So with that, I'd like to thank Sam and Kat very much for their presentations, and everybody for participating and for the discussion. And I'll hand it over to Tony.
Yeah, thank you, Wilbert, and thank you, Sam and Kat, and everyone for joining. As Wilbert said, I just dropped a link in the chat to the event page for the May meeting on the NASA SASE project. So would love to see you all there. We'll take a little bit of a commercial break in April. Then as far as the meeting today, again, just a reminder, this meeting was recorded, so it will go up on the event page where the registration was, as well as it'll be publicly available on IARPIC's YouTube channel. So we usually like to get those up on Thursdays. So if not today, within the week, that link will be live. But yeah, thank you all for joining today. That's all from my side.
All right. We'll see you all in May then. Thank you very much. Have a good day.
Thanks, everyone.